So I'm proud to introduce Jen Mankoff and my PhD student, Julia Schwarz, who is going to defend her dissertation entitled Something About Uncertainty. I'm not sure.
You pay more attention for the rest of these.
I'm going to try to make it
Yeah, I can ask a question about it later. So in addition to Jen and myself, we have Nikki as part of the committee, and then sitting inside the Microsoft Surface here is Andy Wilson from Microsoft Research. And with that, I will let Julia take over.
Okay, Scott, thank you very much. Thank you also to everybody who came to my defense, and especially thank you to Andy, who's taking the time to Skype in, and also to my mom in the back, who flew all the way over to Seattle. Thank you. So today I'm going to be presenting my thesis topic, Monte Carlo methods for managing uncertain user interfaces. And I want to start off with a statement that I think we can all agree with, which is that interfaces are not as smart as they could be. Of course, this is a pretty broad statement, so let me narrow it down a bit. Specifically, I mean that user interfaces don't take into account all the information that they could when making decisions. Let's look at an example, touch input. When we touch a screen, we don't just touch a single point, we touch an entire area. And our intended touch location could be anywhere inside this area, or even possibly slightly outside the area. Yet, by and large, most user interface systems boil this down to an individual point. And furthermore, there's a lot more signal available about our intent outside of just the touch. For example, what was I pressing on before? What are the contents of the buttons? Most interfaces don't take this information into account. And the primary reason for why interfaces are not smarter is because user interface systems do not deal with ambiguity and probabilities very well. They make a single decision early on, and they go with it. To better understand why this might be the case, let's actually look at how a user interface works. This is a very simplified version. Here's a chart describing the process that an input goes through from the moment that you touch a button to when you see it actually light up. I like to call this the input action feedback loop, or just the input loop for short. Some parts of this input loop are handled by the user interface toolkit, or the system, and some parts are handled by application developers, the people that actually use toolkits to make user interfaces. Let's say a user gives some input to the system. She has some intent in mind. For example, she wants to press a particular button. The system then receives measurements from sensors, and because these measurements are imprecise, as for touch, there are actually many possible intents that this one measurement could indicate. Think of this sort of like the touch area. The user's intended location could be one of many possible points. Now, before the input even gets dispatched, right away, this collection of possible intents gets boiled down to a single value, a single input event. Think of this sort of like the entire touch area getting boiled down to a single point. This point is now an input event, which the system can now handle. So the system sends this input event down the hierarchy of interactive elements. This is called input dispatch. And this continues until one interactor marks the event as handled, at which point dispatch stops. And every interactor that actually receives the event might in turn do something, for example, update its state, or possibly update the state of the interface. Now, as part of this state update, the interactor might execute an event callback, which developers write. And this callback might also update the interface state or the state of the entire application. And this is where we hit our second problem. And that is that if any ambiguous interpretations arise, for example, that a move event could indicate one of multiple possible gestures, it is now up to the application developers to handle this ambiguity. And this can be challenging. So, after the event callback has updated the interface of program state, the interface system then draws feedback to the user representing this new state, and the user responds to this feedback, and the cycle begins all over again. So, why are user interface systems built this way? Well, these systems were designed in the time back when the primary input types that we dealt with were mice and keyboards. And these mice keyboards have very low ambiguity, and our existing input systems work very well for these types of input. Now, input technologies such as gesture, voice, and touch input, which do have a lot of uncertainty, were not really prevalent when UI systems were first being developed. But, as you all know, they're becoming more and more common. So what's happening now is these uncertain inputs are being squeezed into this old framework we have of unambiguous input. And this does two things. First, it limits the ability of these new input modalities to infer our intent. And second, it causes applications to have to deal with a lot of complexity as they try to deal with ambiguity and uncertainty themselves. The aim of my dissertation is to change the user interface architecture to better adapt to these uncertain inputs. And it does this in two ways. Let's go back to that input loop diagram I showed you before. First, by considering input alternatives and probabilities at the system level, the toolkit abstracts away much of the complex probabilistic reasoning that was originally put on the developer. Now the developer doesn't have to think about all these alternatives and their likelihoods. And second, because now the system is directly handling ambiguities and probabilities itself, it can now take these ambiguous inputs, and keep this information about interface alternatives and their likelihoods around for much longer, and thus make better decisions. So the contributions of this work are as follows. First, I present an architecture that allows for the incorporation of uncertainty in user interfaces. Second is an API that allows developers to build probabilistic interfaces without needing to think probabilistically themselves. Third, I present a system for generating feedback, which can give continuous feedback about uncertain interface state. And finally, I present a large collection of interaction techniques and applications that demonstrate the value of using this uncertain toolkit. Okay, so here's an outline of the talk. After going over related work, I'm going to give an overview of my system. Oops, forward too early there, sorry. And then I'm going to spend the bulk of my time actually explaining the system to you in a way that's as understandable as possible. And then I'm going to show some interaction techniques and applications that we developed in order to validate the toolkit, and again make some concluding remarks. Alright, so let's talk about some of the existing work. Existing systems for handling ambiguity fall into three general categories. First, we have multimodal input and input fusion systems, and these aim to reduce the uncertainty in interpretation by combining inputs from multiple streams. A classic example of this is Bolt's Put That There system, where Bolt combined where you were pointing with what you were saying to reduce the ambiguity of the speech in the pointing detection. And actually one of my committee members, Andy Wilson, also built a system called XWAND, which used a Bayes net to combine multiple input sources as well as past user actions to better infer intent. The second category of existing systems is input architectures for directly handling ambiguity. And this is actually work done by my advisors, Jen Mankoff and Scott Hudson. And Mankoff's dissertation presented a system that, like mine, maintained recognized alternatives for as long as possible, potentially deferring or mediating actions based on which alternatives were present. Now, one big difference between the work that I'm presenting and Mankoff's work is that the toolkit that I built explicitly tracks interface alternatives and, more importantly, their likelihoods. And then it uses these likelihoods to guess what should happen when input is ambiguous. And the final toolkit I want to mention is a work by Williamson, and this treats user input as a fundamentally uncertain process. Like the work presented here, Williamson uses Monte Carlo methods to implement the inference, feedback, and control systems for his interfaces. And while Williams' system directly tracks probabilities, the system is radically different from what we're used to in conventional toolkits. And while it's not necessarily a bad thing, it definitely limits the adoptability of the approach. In contrast, as you'll see, our toolkit aims to be as similar as possible to conventional user interfaces. So if we look at each of the works outlined below in terms of several dimensions, for example, whether they provide mechanisms for dispatching input, whether they're familiar to developers, track alternatives, and track likelihoods directly, we can see that while collectively the previous work sort of does span all of these areas, no one piece of work covers all of them, except, of course, my toolkit, and this is sort of the benefit that my toolkit provides. Great, so now I get to talk to you and explain how this works, and I'm going to do my best to explain this to you. It's a moderately complicated system, but it's not that bad. You will likely have questions. Please feel free to ask at the end. Or, of course, you can read my dissertation if you'd like. I tried my best to be as detailed as possible there. So let's go back to that conventional input action loop that we talked about earlier. And actually, the probabilistic inputs toolkit's loop is actually not that different. It's very similar. However, in a probabilistic world, we're now not tracking a single input event, but we're tracking a probability distribution over possible input events. And similarly, instead of tracking a single user interface, we are tracking a collection of possible user interfaces along with their likelihoods. So we don't have one interface, we have a probability distribution over possible interfaces. And now, since we're dispatching multiple possible events to multiple possible interfaces, we now have a distribution of possible interface update operations that might be executed. Now, since multiple update operations are possible, we can't just execute all of these at once because there might be conflicts between them. Therefore, all of the update operations and their likelihoods must be considered, and a decision must be made as to which possible update operations to execute and which ones not to. So now that we have this distribution of possible interfaces, the final challenge is then to take this distribution and somehow render it to the user in a meaningful way so that they don't get confused. So, how does the toolkit do this? Well, our system accomplishes this by simulating a probability mass function or probability distribution using samples, just like Monte Carlo methods. Essentially, you take a probability distribution, you look at a bunch of samples that mimic this distribution, and then you see what happens to every single one of these samples, and that sort of gives you an approximation as to what would happen if you sent this probability distribution through a process. So, collectively, this collection of samples here sort of tries to mimic the actual probability distribution. And when applied to input handling, this allows us then to turn probability distributions in each of these phases of the input loop into a large collection of samples. And collectively, these samples represent a distribution over values, but actually from the developer's perspective, all they need to worry about is a single row. In other words, they only need to worry about a single interface alternative. Okay, so now I want to give you a brief demonstration of a metaphor, and the thing I like to bring in is always talk about juggling. So think about a single ball. I think most of us can probably do this, right? Just throw one ball back and forth. And this is sort of what developers have to do in my system. They just worry about a single interface. Now what the system is doing is it's actually tracking all of these balls at once. So it's tracking all possible interfaces. So again, when you think about my dissertation, just remember one developer, one interface, and then the system is doing all of them at once. Yes, so that's the analogy. And of course, this allows us to do a lot of really interesting things. So let's actually go into the details of every section one by one. And we're going to start with event modeling. Probabilistic input events are just like regular input events, except for that they can have uncertain properties, and they can, of course, have a likelihood. So in other words, the variables might follow a distribution. Note that, of course, regular input events can also be probabilistic. They just have a likelihood of 1 and no uncertain properties. To better explain event modeling, and more importantly, the later parts of this dissertation, I'm going to use a simple example of a draggable icon. So let's consider the following scenario. I press down on this icon, move it, and then release it. Okay, so what would the input events look like in a probabilistic toolkit? Well, when I press down, a probabilistic touch event is generated, and this has a likelihood, and a location, which is a random variable. So what the probabilistic toolkit does is then it takes this event and generates some number of event samples from it. And these samples follow a distribution given by the location property of the event. The sample weights here are communicated via the circle's radius, and as you can see, these samples closer to the center of the finger are larger, meaning that the samples are weighted according to their likelihood. And of course, the sample weights are actually adjusted according to the overall likelihood of the actual input event. That's actually it for event modeling. It's fairly simple. So the toolkit essentially gets an probabilistic event, and then it generates a collection of event samples approximating its actual event. So now let's move on to what happens when the samples are actually sent to the collection of possible interfaces that the toolkit is tracking. As a refresher, we'll go back to a conventional input system here. And in a conventional system, we have one single event alternative, which is getting sent to one single possible interface, as we saw before. In our framework, we're not tracking just a single interface. We're tracking a collection of possible interface alternatives and their likelihoods. Each interface in the diagram you see here represents a different possible interface. along with its likelihood on the bottom here. Now, every single event sample that arrives gets dispatched to every single possible interface. For the sake of explanation, let's just consider what happens to a single input event sample. Each sample is first copied and then dispatched to every single interface alternative. Note that since every single interface alternative is different, the event might actually end up being dispatched to different interactors in every different alternate interface. This may in turn lead to several possible different update operations. And as we can see here on the left, a single interface alternative handling a single possible input might actually yield two possible different update operations. And I'll explain why this is really interesting later on. So all of these possible update operations are then aggregated by our system and stored until the next step of mediation, which I'm going to describe later on. So let's go back to this drag room example, and this time, rather than assuming that we have one possible input event, we're going to assume that we have only one possible interface alternative. And let's further assume, for the sake of simplicity, that the draggable icon is the only interactor in the interface. The touchdown event also generates only 3 event samples, which is way lower than what would actually happen. So every event sample is then dispatched to what can be thought of as a copy of every single interface alternative. This is not actually how it's implemented, unfortunately, but it's a good way to do it. So let's look at what actually happens when the draggable item receives every one of these event samples. And to give you a sense of what the developer needs to be thinking of, what the developer's perspective is, let's actually consider the behavior that the developer specified for this draggable icon. It's actually pretty simple. When a user presses down on the icon, the interactor goes from the start state into the down state, and the update operation that it executes is just to show feedback to update the interface, essentially to make the icon look compressed. Then, as the user moves the icon, the interactor stays in the down state, and the update operations that are happening on the interface are just changing the location of the interactor. And finally, upon release, the icon is then dropped, which might execute some external actions. For example, might move a file from one folder to another, and the interactor goes back to the start state. Okay, so that's what the developer has to specify. So now look at what this happens at the system level. So 3 event samples are generated, as we saw, and 2 of them are in the bounds of the interactor, and 1 is slightly outside. Every event sample is then gets sent to the interactor, and remember we have only one interface alternative here. And this in turn leads to 3 possible state update operations. So in the first 2 cases, since the interactor is within the bounds, we have this new state machine update where the state's now in the down state. And in the third case, essentially nothing happens because the event sample is not inside the bounds of the interactor. Now if we look collectively at this set of possible update operations, we can kind of say that now the distribution of interface alternatives is that we have one interface alternative where the interactor is in the start state, and this is with likelihood about 1/3, and we have another interface alternative with the interactor in the down state, and the likelihood of this interface alternative is sort of like 2/3. Or at least that's what's the update operation that we communicate. But of course, really what's happening is we just have these event samples that we're tracking. So again, as a reminder, while the system is tracking all these likelihoods and all these alternatives, all the developer has to do is actually specify that same state machine that I mentioned before. And this is actually almost identical to what a developer would have done anyway in a conventional interface. However, one very powerful thing about these state machines is that you can actually do a lot more than just specify a regular state machine. You can actually build much more complex interactors using the state machine description. And this is done using 2 mechanisms. The first mechanism is that transitions on these state machines can have probabilities associated with them. And when such a probabilistic transition is taken, the resulting interface likelihood of this resulting transition is essentially proportional to that transition's weight relative to other transitions. And in addition, this probability isn't just a number. It can actually be a function over the interactor state or the larger interface state. And this is quite powerful. And it allows us to do stuff like, for example, change the likelihood of a transition based on the value of a button, or more importantly, to incorporate things like user behavior models directly into our interfaces. In fact, as you'll see in a few demos, we actually implemented something that adjusts the likelihood of the transitions based on users' past actions. Essentially, it made the last action much more likely to happen. Another interesting feature is that now we can have multiple transitions out of a single state on just one input. So in this example state machine we have here, we can have two possible transitions on the mouse down event into two different states. And in this case, what the system does is it's actually automatically tracking both of these alternatives as alternate interfaces. And by default, the likelihoods are equal unless the relative transition rules are specified as different. And this is really great because now it allows developers to track alternate interpretations without having to do any of this work themselves. This is essentially abstracted up into the interface system because of this. Okay, so that's sort of the interface update and state machines work. So by now, all event samples have been dispatched to all possible interface alternatives, and we have a collection of possible interface update operations that might happen. Now, in many cases, we can just execute these interface update operations in different separate possible interfaces. However, in some cases, we might have conflicts. Or update operations might actually change the program state. In that case, we can't actually simulate these in parallel. You can't, for example, both save a file and discard it at the same time. So up until now, our system has been tracking all possible events and all possible interfaces, but at some point, a decision does have to be made. And mediation phase is this decision-making process where actions are either accepted, rejected, or deferred. In order to determine which type of update operations can be executed in parallel and which update operations require unambiguous state, our toolkit makes a distinction between a local and a final update operation. Local update operations affect only the interface state, and they can be reversed or canceled just by discarding a particular interface alternative. Now, in contrast, final operations might update the actual program or application state, and this is not samples. We're not tracking many possible programs here. So thus, reversing the actions will be much more difficult. Local updates can essentially be tracked by tracking interface alternatives, whereas final updates require a deterministic certain state. So going back to our drag example, let's see where the local and final update operations are here. So when I press down, the icon down update operation is just changing how the interface looks, so that's a local update. Similarly for a move, let's say for this example that we're only changing the interface. So again, this is just a local update. However, for the release, let's say that dropping the icon might cause some sort of external application action. For example, we might move a file, as I mentioned, from one folder to another. So this then is a final operation. So then the goal of the mediation system is essentially given a list of possible update operations to determine which ones to execute, which updates to cancel, and which ones to defer. Now, the details of how this is actually done is a little bit involved, and many different algorithms are possible. Luckily, we have a very pluggable mechanism so that you can switch out different algorithms very easily. But in general, a mediator will accept all update operations if they're all local. In other words, they only affect the interface. If one update operation is final, and it's much more likely than the others, that one will get accepted, and since this now has to be in a certain state, everything else is rejected. And if, however, multiple possible actions are final, and they are too close to call, then we need to do a separate process, which is called deferral, and a separate interface might need to be shown in order to the user asking them to do something good. So let's actually see what happens now if we're not dragging a single icon, but many possible icons. When we press down, every icon might send an update request. And one detail I didn't mention is that update requests are actually aggregated together, so similar updates are combined, and their likelihoods combined. Thus, since more samples hit the green item, this one has higher likelihood than the rest. And because all these requests are local, they're actually all accepted. Thus, we're basically tracking 5 interface alternatives, one for each item being directed. And as we move, the same thing sort of happens, will be granted. However, when it's being dropped, these actions are now final, meaning that only one alternative can be selected. And in this case, the mediator sees that the green icon is much more likely than the others, and so the interface alternative containing that green icon as the interface that's being moved is set as a certain interface, and the state is now deterministic, and we can move on. The icon gets dropped, and the code to execute, for example, the file move, then gets run. Of course, if it's too close to call, for example, let's say somehow the icons were much closer together, then we have to go through a separate deferral process, and we might have to show a separate interface. And the details of this part are in the thesis because I don't have time to cover it, unfortunately. So after the mediator decides which actions to accept and reject, the system now has to update its distribution of interface alternatives to reflect these update operations. So I'm going to describe how this happens. It's not too complicated. So let's go back to that example where we had the state machines with the event samples and see what requests they executed. So we had 3 possible requests here. 2 of them were for the icon downstate, and the last one is essentially a no-op. And all of them have roughly equal probability, and they're all local update operations. Now these update requests actually contain several things. They contain the event samples that generated the request, along with the interface alternative that they came with, and of course the actual update function that executes the operation. And since all of these are local actions, they're all going to be accepted. So what happens now is that for every accepted action, the system first generates a clone of the interface that caused that request, and then it executes the update code in the context of this new cloned interface. And the old alternatives get discarded. Then the likelihood of every interface alternative is set to be the likelihood of the particular update request, which is in turn set based on the event sample likelihood and the transition likelihood. So this new set of interface alternatives now approximates this new distribution over interfaces. And now we have a set of samples that approximate our distribution. Now in this very simple example, we only have 3 interface alternatives, but of course in many cases there may be hundreds, maybe thousands of possible samples. So we need to reduce this number in order to make it computationally tractable. So we do this in 2 ways. First, we combine interfaces that are sufficiently similar, and the details of how we determine this are discussed in the thesis. And of course, our likelihoods get combined as well. And then even then, we might still have too many interfaces to deal with, so we actually have to downsample that amount to a smaller, more manageable set. In this case, we only had 2 interface alternatives, so we can just move that along. But in many cases, we'd actually have many more, and then we'd have to downsample accordingly. So now we have this new distribution, which represents the distribution over possible interfaces. And what about the case where only one alternative was accepted? I'll briefly cover that here. It's pretty simple. As I mentioned before, the rejected actions just don't get executed. Those interface alternatives don't live on, essentially, they die. And the one accepted action does get continued on, and it does get updated. So now we basically have a single interface alternative with a likelihood of 1, and that's now our new deterministic interface. Okay, enough theory, let's see some examples. So in this example, the pink box is draggable, while the green box is draggable and resizable. And on the left, you can see the main interface here. And what we're basically seeing is all the possible interface alternatives are sort of overlaid on each other, and the likelihood of every interface alternative is communicated via opacity. And on the right here, we're actually seeing all the interface alternatives that are being tracked. And of course, this is after downsampling, or after sampling down, because you can only see 2. There's actually way more. You see a mouse here, but the icon that's jittering around is actually showing one of many, many possible event samples that are actually being sent here. So what we can see here is we're seeing 2 possible outcomes here. In one case, the green eye is being dragged, the other one, the pink one, is being dragged, and the likelihoods are above. And then when I release, as I mentioned before, we now have to go to certain states, the more likely item is picked. This one's really cool, because we're actually tracking both the likelihood that's being resized and dragged. Of course, it went away. So it sort of shows the power of this sort of framework. Okay, let's actually see a more extreme example. In this version, we're tracking many alternatives. So first, this box can be dragged or resized, or we might be painting on the canvas directly underneath here. And so you can see here that the system's basically tracking all these alternatives all at once, and also updating the likelihoods of every single interface alternative as you get the new events. Okay, great. So now we've generated a collection of event samples, dispatched every event sample to every possible interface, obtained a list of possible update operations, picked which update operations to execute, which ones to cancel, and updated our distribution over possible interfaces in order to get a new distribution over interfaces. Final challenge is to render this distribution of alternate interfaces to the user in a way that's not very confusing. Now, our main goal when designing this feedback mechanism was to enable the communication of these alternate states without actually requiring the developers to change how they do their rendering logic. In other words, developers should just be able to draw their interfaces like they did before by implementing a single draw method. And then what we decided is we'd allow developers to change how uncertainty was communicated by changing which feedback object they use when rendering the interface or writing their own. Okay, so here's basically how we did this. So as you know, the input to the system is a collection of possible interface states. We then reduce this set of interfaces to a set of representative snapshots, and fuse these snapshots into a single interface here. Now this interface might actually contain parts from different possible interface alternatives, and also might have containers that actually change how these alternatives are rendered based on their likelihoods. But the reduced set is just an interface, meaning it's just drawn to the screen as any other interface is drawn. And each of these stages, reduction and fusion, is pluggable so that developers can mix and match different methods to get maximum flexibility. Okay, so as you know, we all start off with a collection of possible interfaces. We already discussed how that happens. And of course, there might be far too many to render on the screen, so we need to reduce this to a more representative set. And several approaches to this are possible. Here are two that we implemented. The first and most obvious solution is just to select the n most likely interfaces and chop off the rest. But of course, we might lose valuable information about alternatives this way. But another approach is actually to cluster interfaces. In our case, we did this according to which properties in the interfaces had actually changed. So if we have, for example, a button that had changed in multiple interfaces, we group all those together. Then you could do stuff like take the mean, for example, of properties of this button. Or, for example, since you can't always take the mean of, say, two strings, you could specify some other aggregation function. And of course, we specified a number of aggregation functions, such as mean, mode, etc. in our toolkit. So now that we have this smaller set of alternatives, the next step is to fuse these alternatives into a single interface that actually communicates the ambiguity across these interfaces. This fusion step is done via a special feedback generator object, which our toolkit provides a library of many of these, but also can be developed by developers. And as I mentioned, we implemented a wide range of these, and by changing which feedback technique to use, drastically different interfaces might be generated. But you've got to realize that these can be generated without actually changing any of the rendering code for the actual interface itself. So here we can see a collection of possible interfaces, and by changing which feedback method to use, we can actually, in the end, output very different results here. So we implemented several different sort of families of these feedback techniques. One of them centered around overlaying alternate versions of interfaces on an interface and then adjusting appearance to reflect likelihood. So here's an example. In this implementation, we overlaid feedback about multiple possible gestures onto the screen and adjusted the opacity of every one of these gestures according to likelihood, just like we saw before. And this yields an interaction technique very similar to Olivier Bau's Octopocus, if any of you are familiar with that. So here essentially what we have is we have a collection of interfaces. Every interface is drawing one possible gesture completion. We just overlay all these on top of each other and possibly use an opacity. So this is a very simple technique. Here's something that's a little more interesting. So in this application, we can drag icons on different targets. The targets are these circles in order to perform different actions on them. And what's actually happening here is actually a probabilistic interface where for every item that's selected, for example here, in one possible interface, it's just the music item that's selected. The interface is actually trying to guess which target it wants, which target the user is trying to drop onto. So it actually shows only one target. So in the interface alternatives, you're actually only seeing one target and one possible draggable icon. And then what it's doing is it's again overlaying these alternatives and compositing them. But what's interesting is that the draggable icons are being composited using just opacity, whereas the target interactors are being scaled according to the interface likelihood in addition to using opacity. And the way that we can accomplish this, in other words, changing the feedback method within a single interface, is essentially to have a context-aware feedback selector object which changes which feedback method to use based on things like the interactor ID, which is sort of how this is done here. So the second family of feedback that we implemented centers around showing alternate versions of interfaces in an n-best list, and then allowing the user to select which item in order to disambiguate their intent. So here we can adjust several different bits of information in our n-best list. We can adjust what information is being displayed, how the user disambiguates their intent, and finally, how uncertainty is communicated. Let's look at a few examples. In this demonstration, I basically have a drawing interface, and when I finish the drawing, I release my mouse. The system tries to guess based on my gesture which shape I intended to draw, and draws that shape to the screen. And this gesture recognizer is not very good, so it actually thinks for some reason that several possible gestures are likely. For example, a circle, a triangle, and there's a path, essentially no gesture at all. And usually when it's confident, it'll just pick the most obvious thing. But when many are likely, it actually will basically show an m-best list, sort of how you have autocomplete in your text entry systems. And then a user could actually select one of these alternatives and change what actually ends up being rendered on the interface here. Now here, we're only showing the new part of the interface, or the interface delta, the thing that would have changed as a result of the action. But of course, we don't just have to show the delta. We can actually show the entire interface, and this is what you see here. So after I draw, in that case, it was very confident that I was drawing a path. But here, for some reason, it thought that I was drawing a circle, because I'm not using a very good gesture. But it can, of course, it doesn't matter that it's not very good, because it just shows its next best guess. It knows that it's not confident. So again, it guesses wrong, but then it shows the alternative, and then I can I can select that alternative and correct it, basically. Now, of course, we don't just have to show the entire interface. We can also just highlight the parts of the interface that have changed so that the user can see more saliently what's going on here. And that's what you see in this example. And here's another example of feedback using an m-best list. And this time we have a predictive menu system. So what's going on here is we actually have a menu that's essentially trying to predict which menu item the user is trying to select using basically a very simple frequency-based model. And so as a result, it essentially generates a bunch of possible interfaces and shows these possible completions on the bottom as an m-best list. The user can then click on this completion or select the alternative using a key, which is what we see here. Press the key. And the last thing that we can do is we can adjust the feedback that's being displayed based on extra contextual information. And that's sort of what I showed you there, where we had the target scale being scaled according to likelihood versus the icons being changed using opacity. We had a feedback item that was basically changing the method of feedback used based on the idea of the interactor. Another example of this is that in many cases we actually don't want to show any feedback at all to the user. We just want to show the most likely interface. And only when the user indicates some sort of indecision do we actually want to show, say, an m-best list or some sort of ambiguity. So in this example, we can draw out a bounding box for one of several shapes, and by default, the most likely shape is shown. In this case, because I'm drawing ellipses, the system predicts that I probably want to draw an ellipse next. However, when I pause, as you saw there, the system actually shows an m-best list. So here you can see again, I pause, it shows an m-best list with completions, highlighting the change in the interface, and then I can actually select that alternative just by clicking on it. And note that what's really cool about the way that this system is implemented is that changing to that particular interface alternative is just a matter of switching the current interface, or the most likely interface, to that particular interface alternative. No extra operations are needed. Okay, congratulations, we made it through the system description. Let's do a recap. We are given as input a probabilistic input event, which we then convert into a collection of event samples. We then dispatch every event sample to every possible interface and obtain a collection of interface update operations. A mediator then examines these update operations and determines which update operations to accept, which ones to reject, and possibly defer. Rejected operations get discarded. Those interface alternatives get thrown out. Accepted operations, we clone the interfaces, update according to those update operations, and we get a new distribution. Now we have a new distribution of possible interfaces, and then this set of alternatives is then reduced and fused according to a feedback object and drawn to the interface so the user can see it. The user sees this new interface and then responds, and the input loop is complete. And now this loop happens for every single event. Okay, so let's see some example demonstrations. As I mentioned before, we validated this architecture by showing a large number of interaction techniques and applications built using our toolkit. And today I'm going to show you a few examples, and to make it historically interesting, I decided to show you examples from all three generations or iterations of the toolkit that were developed throughout my time as a PhD student here. The first example that I'm going to show you was built during my first year and was implemented on Windows laptop with a touchscreen.
Window resizing is often difficult in touch, and is even harder when the window is on top of an icon, because it is impossible to know whether the window edge or icon is the user's goal. In our framework, window interactors are augmented to understand that horizontal motion is highly indicative of a resize event, while vertical motion is not. Thus, when a user moves her finger, the window resizes if she moves horizontally, whereas the icon moves when she moves vertically or diagonally. Conventional sliders are often difficult to manipulate because of their small activation area. Our framework allows a slider to be activated even when the press isn't directly over the slider. When multiple sliders are nearby, they may all receive mouse events and show feedback. When entering text into a form, although the text entered is certain, where this text should go is often ambiguous. The text fields in this example show feedback in appropriate text boxes as the user types. A user can then continue typing or select the correct text box. Voice recognition systems often output multiple interpretations with different confidence levels, something current frameworks have a tough time handling. As the following example illustrates, our framework easily supports this by delivering all possible interpretations of voice events and allowing the interactors to determine what they should show, similar to the previous example.
8. 8. 2. 3. Ball.
Okay, so that was sort of the first iteration. I also should mention that every single iteration involved sort of a slight reworking of the toolkit until the final version, which is sort of the toolkit that I presented today. The second iteration was done somewhere like in years 2 and 3 and was implemented on Windows Phone. You're going to see it here. It's essentially a drawing application with a lot of ambiguity.
Our framework allows developers to simply combine these interactors using basic application logic to create an application which appropriately handles ambiguity, not just within interactors, but between interactors. It just works. When a user accidentally grabs a stamp while gesturing, Canvas and Stamp work in concert to show appropriate feedback and prompt the user to continue gesturing, whereas a conventional input system would have forced the user to restart. By using a sample-based approach, our framework enables complex interactions which handle ambiguous scenarios largely without requiring the developer to think probabilistically.
Okay, and here's one more drawing application that's even more, I think, interesting, and that was built this year using the final version of the toolkit.
Consider this touch diagramming tool inspired by Igarashi's interactive beautification. Users add shapes to the canvas by dragging out a bounding region. Multiple shapes are possible. The application guesses the most likely shape based on past actions. When the user hesitates, the application shows an best list highlighting changes. The user may then select an alternative by tapping on it. Shapes and lines may be dragged. When an item is being dragged, a trash can appears at the bottom of the screen. Dragging to this area removes the item. Of course, if the user just wants to put the item at the bottom of the screen, she can select this alternative as well. In addition to being dragged, shapes can also be resized. When adjusting lines, endpoints snap to targets. Here is a demonstration of the features of this application. Such an application would be very difficult to implement in a conventional interface framework. With our framework, both the tracking of interface alternatives and the rendering of these alternatives to communicate uncertainty are handled by the system. Interface developers only need to worry about specifying the operational logic of interactors and about rendering a single alternative to the screen.
So with that, I'm almost out of time, looking at the clock here, so I'd just like to conclude by wrapping up and saying that this thesis presented a new architecture for handling uncertain input, and importantly, the API that's presented allows for developers to build these probabilistic interfaces without actually needing to think probabilistically. They can essentially build interfaces as they have before. And there's a lot of work left in this area, a lot of limitations and future work. But I hope that this architecture provides a foundation for hopefully this new era of user interfaces that embrace uncertainty to better infer intent. And with that, I'd like to thank you all very much for listening and take questions. That's it.
So we will start with questions from the committee, starting with Andy. We probably need to unmute Andy.
He unmuted himself.
Needs to be a
I can barely hear you, but I'll speak to the audience. Yeah.
Okay. I'm sorry I couldn't make it. I really wanted to attend this in person. I need a lot of feedback here.
Oh, I see. Let me mute myself. One moment.
really quite comprehensive, and I really enjoy the whole package. It's great to see end to end. You limited yourself to what you were calling conventional interfaces. Now, the advantage of that, of course, is that people can look at this stuff and understand that you're not trying to solve all the world's problems and proposing something that's completely new, at least in the way that it looks and the way that it works. But so the last time I read through your draft, I was on the lookout for aspects of the toolkit that are actually tied to conventional user interfaces, and I was wondering if you could speculate on whether the toolkit is actually more general than what you than how you pitch it.
Okay.
Or could you use that, use your toolkit to model spoken dialogue systems or human-robot interaction, or some of the stuff that Eric Horvitz and Dan Bogue have been working on. And I see a lot of commonalities, and looking at Dan's work and your work, I feel like you guys are working on fundamentally the same problem. And so I'm wondering, are there components of your system that are really tied to these very familiar conventional user interfaces? Maybe that's a long question.
Okay.
Please feel free to speculate.
Okay, so the question was that we've sort of tied ourselves to conventional interfaces. In other words, we tried to mimic conventional interfaces as much as possible. And Andy was wondering if the toolkit actually, or this approach of tracking many possible alternatives, is more general, and if really he sees a lot of similarities between work in human-robot interaction, and he's wondering if really we're doing the same thing, and also whether if we removed ourselves from the bounds of a conventional interface, if we could do a lot more. And he also asked about spoken dialogue systems. So to answer the question, I'm not deeply familiar enough to speak to exactly the similarities of my system to, like in detail, the systems of the spoken dialogue management system. But I mean, I think the ideas of the toolkit is, if I was to generalize and sort of take a leap, there are differences because I thought about this a lot, but essentially we're kind of running particle filters over user interfaces. It's not exactly the same. In the thesis I mentioned how they are very similar, but they're not exactly the same, but there are definitely a lot of similarities. And so I do see that generality, and I've constantly been seeing it, but every time I try and model it exactly as a particle filter or exactly as this general thing, I can't quite make the leap. It doesn't mean it doesn't exist.
Well,
Go ahead.
What kind of challenges have you seen before you tried that?
I always get stuck on the event update part. So essentially, you're updating. You have this model of a system where each of your particles has like a motion model, and then it has a measurement model. And I can kind of figure how the measurement model matches with when you sense something, the likelihood that your measured input matches the current state of the interface. That's great, but I always struggled. In an interface, we have this thing where our input updates the state of the interface. So we've got this relationship between input kind of communicating, measurements essentially communicating or giving us information about our current state, but also updating the next state. And I never quite figured out how exactly to parallel, or how exactly to fit that in perfectly. But as I mentioned in the thesis, I did actually devote a section because I realized, okay, we can use these probabilistic state machines to essentially simulate a particle filter. I talked about that in my thesis, I believe. If I didn't write it in the thesis, I definitely intended to, and I can update it. So, but I'm not sure if I answered your question. I think it's probably possible to do a lot more. I mean, it's probably possible to do a lot more. We did for this toolkit, but what's interesting is, especially as I started thinking about the power of probabilistic state machines in particular, I started realizing that you can do a lot with probabilistic state machines just by themselves. And I started getting all these ideas, but I didn't have time to implement them all, because it's actually kind of hard to implement these things. An interesting challenge for future work is debugging probabilistic interfaces. It's kind of hard. I sort of had some techniques, but anyway, that's a digression. So my answer is, I think there are some similarities, and I started to look into it, but I didn't have time to delve in and make it more general.
Okay, thank you.
Thank you.
Do you guys want to go round robin, or should I ask another question, or?
Go ahead and ask another question.
Okay, so, you really haven't talked about usability, and, you know,
Yeah.
it just seems like that's a thing that
Elephant.
someone's gonna have to do with
Yeah.
usability.
Yeah.
I was wondering if you could just speculate on, oh, and you've also made the point that developers don't really need to think about uncertainty when they're putting these systems together, which sounds magical and probably unrealistic to me, but okay. But then what about the user? Do you think the user is gonna be able to handle these probabilistic interfaces
Yeah.
in a you know, a sufficiently complex user interface, like, I don't know, like Word?
Okay, yeah. Okay, so the question was, what's the usability of all these probabilistic user interfaces in a nutshell? And he also mentioned the point that I keep on mentioning that it's actually very easy for developers. They don't have to think about probabilities. And while I think it does simplify it a lot, there are definitely some specific challenges that I think developers do still need to worry about, is that when things don't go exactly as you want and you have to debug the interface, then it's challenging. And I did build some tools to debug interfaces for myself, which was essentially to show these parallel states. But debugging is still, it is sort of difficult, but I would posit that it would be even more difficult and almost intractable if developers, every time they built a new interface that had to handle probabilities, if they had to build all of that infrastructure themselves again. So back to the usability. I didn't mention, because I didn't know if I would have time in the limitations section, that is one of the big limitations of this work right now, is that we don't have a usability evaluation in it. And while I think that validation by demonstration is sufficient for the contribution of this work, which is in an architecture, it's definitely something that needs to be considered. So in many of these cases, for example, overlaying interface alternatives using opacity is not a very good way to communicate uncertainty. And that's why a lot of the earlier toolkits I thought had some very big limitations, because all the demonstrations essentially just overlaid alternatives using opacity. But in the later work, one thing that we did do, which I thought was really interesting, is that by default, we just would show the most likely interface, or some default interface. And then only when the user indicated some form of hesitation would we actually show any alternatives at all in the form of an best list. And this sort of reminds me, the way I like to tell people about this is it's sort of like autocorrect or an best list for typing, in that usually you can just go about your business and not worry about it, and then when you need to disambiguate, you can, and you can do that just by pausing your interaction, or if that's too much, you could just press a button somewhere and have the alternatives show up in that case. So actually, I think the most usable form of probabilistic interfaces is not to show anything until the user actually wants to disambiguate, essentially, by indicating some cue.
Okay, thanks. I think I passed the conch.
Okay.
All right, well, Andy stole my questions. Okay, I'll sort of like go into more detail, but I guess two kind of high-level pieces of feedback. One, that was awesome, really interesting work. The other is, this is a thesis defense, not just a proposal, so like I think you should probably have done a little bit more in terms of like flaming torches or something,
Okay.
instead of balls.
I'll tell that to the next person that's defending.
I think maybe we should think about that as a requirement. Some kind of dangerous object or something.
Nice.
Yeah, right.
I can do
Nice.
that.
Come our way.
Yeah, okay.
What about flaming torches?
You could put like a bulletproof glass or something. Okay, so my question. So one question I have, I kind of want to probe, because I don't fully understand it, this idea of the developer doesn't need to keep in mind all the uncertainties. So it seems like in a lot of the examples you gave, I'm trying to figure out like where is that actually true, and what do they need to think about? Because in some ways, it seems like you need to think at least a little bit probabilistically in order to represent that uncertainty appropriately in the system. So does the system take the right kind of actions? Does it provide that feedback in the right ways? So could you talk a little bit, I'm just thinking about even in all of the different phases, like if you give a touch event or if you get a pixel as an event, right, do you know, the probability distribution is probably going to be different depending on if it's touch or if it's a mouse click, and is that handled by the system?
Yeah.
Is the, when you show things about like resizing versus dragging, and resizing is usually like a horizontal thing, is that built into the system? How about these like dependencies and transitions in your probabilistic state machines? Like, do developers really need to understand what those are and how to specify them, and like local versus final updates and the impact of those across all of the kind of interface components that you're doing? So, I don't know, can you just help me think about like what is the toolkit doing and what do the developers need to do? And is this do they need to think about this differently in the same way that, we have to teach people how to program in parallel? It requires a slightly different way of thinking.
Right.
So just help me make those connections.
Yeah, that's a great question. And also, the last point that you talked about in terms of the programming parallel, I think sort of touches on the distinction that we have here. So, going back to the example of touch versus a mouse. So, what the system is doing is allowing so that developers don't have to manage any of the logic around tracking alternatives. So for example, if the distribution for a touch input is different than a distribution for a mouse input, the developer shouldn't need to have to worry about that. All they need to worry about is that they're handling pointer events in general, and that the distributions will be appropriately handled, and they just need to specify the logic essentially of the state machine. So in other words, how to react to it. So if the distribution is different between touch and mouse, the system handles that part.
And you build that in? You have that built in?
Yeah, that's built in because the system actually is the part, whoever is in charge of making the interface for the mouse events and the touch events specifies the get samples method essentially, which returns a list of samples for a particular event. But that's not usually what the people that are writing the interactors are worrying about. So in terms of going to the state machine, so a developer would need to understand, for example, so they don't have to understand probabilities at all. As I mentioned with the draggable icon example, in the very first example, the developer essentially specified a state machine that was exactly what they would have specified normally, with the one exception that they need to specify a distinction between local and final actions, whereas a local action just updates the interface, final action updates the application state. And so they don't have to, but they can manage, so they don't have to deal with uncertainty, but if they want, they can go a little bit deeper. But still, what you're having is you can take these sort of the advantages of maintaining multiple alternatives and probabilities, but what we're abstracting away is that actual management of those uncertainties. Sort of like how in a multi-threaded system, the system that's actually handling multiple threads is dealing with the scheduling and actually the execution of one instruction than another from a different thread than another. And it sort of abstracts away that part. So the developers just have to specify, here's a thread and here's what it does. So developers still need to understand that in that threading model, what it means to have multiple parallel threads and what it means, for example, to have an object. If an object is accessed by two different threads, what could happen there. But the system is actually deciding which commands to execute when. And that can be abstracted away such that multiple CPUs can be handling, etc. And in sort of the same vein, developers with a probabilistic system need to understand what it means when you have two transitions out of a single state with an identical with identical inputs. What they need to understand that will essentially result in two possible parallel interfaces, but they don't need to worry about the management of those actual interface alternatives because the system actually handles the management of the alternatives, and the developer just specifies the behavior. So it's exactly like the threading model. The system handles management, but the developer needs to specify behavior. But I think the statement that the developer doesn't need to think at all about probabilities can be reworded to say that they don't have to think about probabilities. That was a long answer.
It's okay, it was a long question. So the other question I have is again, this is going to what Andy was getting at around usability, and we know a lot. so there's actually a lot of work showing that people really hate the idea of an uncertain world, and they will think that the world is deterministic, even if there's good reason to believe otherwise.
Yeah, I struggle with it. Yeah, I know. Yeah.
And so we've seen things like, okay, I'm going to set this up as a straw man, which because I don't actually believe this exactly, but if you see what Microsoft did with Microsoft Office 2003, they had these adaptive menus that like hid.
Okay, it was 2003. Yeah, Sandy mentioned that too. And I was like, which version? Mm-hmm.
Yeah, and so like they got rid of that because people hated it. And in part because you're sort of breaking the model of what the user has of the world in their head. And so there's issues around kind of like changing their mental model. There's issues around like, I have to sort of track that I have two possible or three possible or multiple possible things. So is there like cognitive overload? So I guess I'm wondering, what kind of cognitive issues does enabling uncertain interfaces bring up?
Well, it could definitely bring up a lot if done wrong, and I think that you're right. In most cases, you shouldn't actually show uncertainty. And the point of this toolkit is that just to enable it such that in the cases where it is important, so that you can actually deal with these alternatives. And I guess my response to the fact that people don't like predictive menus is then to ask, why are people okay with autocorrect on typing? Like, it's also a corrective system, right? And why can't we bring the same ideas from autocorrect? Or, everyone seems to love the NBEST lists that are shown up when you're typing, right? And they've sort of accepted the fact that the system, the buttons are really small and it's kind of hard to figure out exactly what you're pressing, and it's just trying to guess. So I think that it's not necessarily that all uncertainty is bad, it's just that you've got to carefully design it so as not to make people worry. And what I found in all the experimentation that I did was that the only way that you can do this is what I mentioned to Andy earlier, which is by default just show the user the most likely thing, which is in most cases correct, and then allow them to correct later. So one example that I didn't show in this talk, but that I did implement, was this disambiguation between selecting text and scrolling. So as you all know, when you select text on a tablet, you have to press and hold in order to trigger the selection. And usually that's because there's ambiguity between whether you're trying to scroll or select text. And I basically built an interface that basically just tracks both alternatives and guesses what you're trying to do, and it doesn't actually require any pause. You just move and it'll magically figure out what you want to do. And then basically, if it was ever wrong, you just pause, and it would show a little, in the left-hand corner, it would show an alternative. It would say, hey, did you mean to highlight? And you just select that, and it just moves to that alternative. So that's an example of, I think, a way in which, and I didn't test this for usability, but my intuition, my subjective sort of evaluation is that that's sort of a way that you can do it. So that's my answer.
Okay, I'll go next. All right, just one question. Three parts. So the root question is this really tractable? But the more specific version of that is, how many samples are you typically using here? And then the third part is, when is this going to break down? You've got an exponential explosion of samples. I know what you do to fix that. But where does that mechanism break? So that's the difference.
Okay, so is it really tractable? So my question to you is, define tractable. Well, there are many things that make it challenging. Okay, since the rest of your questions were around computation, I'm going to just answer the question, is it computationally tractable?
That's what.
And my answer is, I believe so, and even if it's not computationally tractable now, I believe it will be in like a few years, or 10 years. And the reasons that I think that it will become, okay, so I will leave the reasons for why after I explain some of the limitations, which I didn't get to talk about in the toolkit, which is that how many samples are we normally dealing with? All of the demonstration applications you saw here and all of the ones in my thesis were, and this is discussed in the limitations section in my thesis now, were used with only 20 samples, which is very small. And essentially, if you go up to a reasonable number like 100, it's currently, with the current implementation, which is not optimized, it becomes just too slow to use. And so the reason that I think, however, this will become computationally tractable is two reasons. One, there's a lot of room for optimization. The slowest part right now is cloning of interfaces, which can be made much faster just by cloning them more intelligently and storing, instead of storing exact copies, using diffs essentially of the data structures. And second, this is a highly parallelizable problem. The cloning can be parallelized, the dispatch of every single event sample can be parallelized. It's not complicated, so in theory it can be run on the GPU, but we all know what's happening with computers, we're just getting more cores, so I really don't think that it's going to be such an issue. And the number of samples, so tractable, number of samples, I forgot the last part.
When does it break down?
Yes.
Oh yes, in which cases does it break down? I think it breaks down in two cases. The first case right now is when you have an input event that is so, yes, in two cases. In the first case, it's when you have an input event that's so ambiguous that it requires a huge number of samples to estimate. And the second case, which I think is probably more important, is when the interface is designed such that there is so much ambiguity that there's just too many, there are many possible states requiring a large number of samples, essentially, to simulate. So the cases where it breaks down is when you really do need many samples. But so this approach of sampling at the interface level is pretty controversial because, yes, there are a lot of samples that in theory you would need. But what we actually found when implementing these tools was that you don't actually need that many samples to approximate an interface because actually an interface tends not to be yet that ambiguous. So that's what we sort of found, but if you do have a lot of examples, then it does break down.
I was wondering what role the passage of time plays in any of the infrastructure you built, and if it doesn't, how you might incorporate time into what you did and what you see as a valuable use of time in dealing with ambiguity.
I don't actually, what role the passage of time, can you explain that a little bit more?
If you know when events, so I'll give you part of the answer. Your example of pause is something
Sure.
that incorporates time,
Okay.
right? So I'm wondering if you see a bigger role for time. Time is also used in animation-based interfaces. So where do you see time coming into what you did? And is there a potential future work that might incorporate time if it's not already a key part of what you're doing?
Okay. Okay, well that seems a little bit general, but I can speculate. So I think I'm not exactly sure what you're asking, but I think that one example of a role that, or something that you could use time for is that you could adjust the probability of some sort of time-based event based on how much time has passed. So you could, for example, if you have alternatives that require quick motion, those alternatives can sort of degrade over time. And another part that time can play, which is hopefully, well, it's an area that you guys certainly are very interested in, is prediction of future events. And essentially, the really cool thing about predicting future events, which we saw a little bit here, was that because a future prediction is just a probabilistic event, you can, of course, just send it down the probabilistic event pipeline and look at the outcomes and render feedback to the user. So those are two cases in which we could use time in the probabilistic event system. But I'm not actually sure if I answered your question because I'm not sure if I answered the question. But I
That's a
can,
fine answer.
okay.
Thank you.
More? Okay. More questions?
I have a question.
Yeah.
So in the condition of using touch, you said like generally you're using like 20 samples to generate different interfaces. So like, is there a specific rule of how you generate the different samples? Like, considering if you are using a finger to touch the touchscreen, is that like probably in a different shape than just a circular?
Yeah. So actually, how do I explain this? So the samples that are, so for example, with the touch screen,